our next speaker is Manuel Gensler from Fraunhofer IAP about overcoming the deficiencies in the micro LEDs. Manuel, please.
Yeah, thanks for the introduction. So, another talk this afternoon about quantum dots. We are now switching from blue to red and green, and I'm excited that I can show you some recent developments at our Research and Development Institute, the Fraunhofer IAP, on the topic of quantum materials with a special focus on micro-LED applications. With me in the room is my colleague Johan Kim, up there. Later for the Q&A session, he can answer further details. So, and when I use the white pointer. So we are actually, so two divisions in our institute are working on quantum dot materials. We are located in Potsdam, which is our main quarter. And we also, since a few years, the former CAN AG is now a member of Fraunhofer, the Fraunhofer CAN, Center for Applied Nanotechnology, part of Fraunhofer IAP. And they also will also include some part of their technologies into this talk. So, I think this slide is quite famous. So that's the motivation why we are doing quantum dot color conversion. As long as the technologies for the micro-LEDs doesn't tackle the green gap with some future developments which have been shown 2 talks before, quantum dots may be a solution to tackle this efficiency gap here, which is for the green, an issue of the indium gallium nitride micro-LEDs. And for the wet ones, the aluminum gallium indium phosphide ones can actually be quite efficient, but due to the long charge carrier diffusion length, when you make them smaller and smaller and smaller, you end up with a final efficiency that is even lower than for green for very small chip sizes. And therefore, quantum dot color conversion technology, although you always lose a bit of the photon's energy doing color conversion, can at the end, on the device level, be more efficient than using RGB micro-LEDs. So this is here some publications using modeling a possible efficiency of a final device using some recent data, and they show here for a VR/AR device, micro-LEDs plus color conversion in yellow could in principle have a higher efficiency in the device than RGB OLED or RGB micro-LEDs, and therefore it's interesting to look at this color conversion technologies. In principle, we think there are 3 different types of quantum dots relevant in this field, which is the cadmium-based quantum dots, which are mainly researched in our Hamburg division. We have the cadmium-free RoHS compliant ones, indium phosphide based, which we are focusing in Potsdam, and also Hamburg is a bit working on this topic. And then there's the perovskite quantum dots, which I find really exciting, but at the moment we don't do focus on this research, so I won't present in this talk today about this type of materials. So I selected 4 different application or development examples for you, which are relevant for micro-LEDs from our quantum dot particles. One is to optimizing the stability using ligands. The second approach is using giant shell quantum dots. The third one is increasing the blue absorbance using some alloyed structure in the quantum dot. And the third one is improving the jettability in the EHD-Jet printing, electrohydrodynamic jet printing. So, the first one, usually they say, show one equation or one chemical formula, you lose half of the audience. So if you're not a chemist, please just ignore the chemical structures. What I want to point out here is there's different types of organic ligands on the outside of a quantum dot. Some are strong bound, some are weakly bound. And if you know how to create your quantum dot using ligand exchange such that you end up with only stable ligands, you have a higher stability of your quantum dot materials, and finally a higher stability of your device. And you, after synthesis, you may, for example, even end up with solvents in your ligand shell, which you want to replace with more strongly bound ligands. And after doing ligand exchange here with a specific type OTT ligand, we could show by increasing the applied material onto the shell.